Hey guys, in this video lecture I'm going to be discussing Thevenin's theorem, talking about what you need, the steps you need to obtain them, and then go over a couple practice examples. Thevenin's and Norton's theorems tend to be a sticking point for a lot of students, myself included, when I was taking Circuits 1. People think that out of all the methods learned so far that they can be pretty intimidating. However, once you get the hang of it, you see that it's pretty simple and that you can transform a very complicated circuit into something that is much more manageable. So let's just get right into it. These steps, by the way, that I have right here, these are all good stuff to put on your formula sheet. Thevenin's will come back later in the semester, and this is also good stuff for the final exam and the lab this week in case you forget a step or what to do. So without further ado, let's just go over them, and then we'll do 2 or 3 practice examples. So R load, the easiest one, this will always be given to you. R Thevenin, how you're going to get this is you're going to short the voltage supplies, open the current supplies, remove the load resistor, and then combine the remaining resistors that will be in series or in parallel. For Thevenin, the last thing that you need, you're going to remove the load resistor, which is going to leave an open circuit, and then you're going to solve for the voltage across that open circuit using nodal or loop analysis. So this is what the remaining circuit's going to look like, and then you can find the current through these resistors. So let's just get into the first example. All right, example number 1. I picked a pretty easy one to start us off with, just to get our feet wet. So let's just get right into it. So R load, the load resistor. Well, we can see that V out is going across this one right here. It's going across this one. So this is going to be our load resistor, right? That's going to be given to you, which is 3.9K. All right, so step 1, done, boom. Step 2, find R Thevenin. We're going to short the voltage supplies. There's 2 of them, so we could just get rid of these easily, just like that. All right. We're going to leave the resistors. We're going to remove the load resistor, right? Just like that. R Thevenin. So this is this tends to be a unique situation where these are neither in series or in parallel. These 2 remaining resistors right here. So what you need to do is you need to imagine putting an ohm meter right here, right? This is A, this is B. Imagine putting an ohm meter right there. And how an ohm meter works is it sends a current throughout the entire circuit. And we all know that current is very lazy. It chooses the path of least resistance, right? Since there's a short right here, all the current's just going to flow through there. I'm going to draw an arrow so that you guys could see that better. So it's going to flow here. It's at a crossroads here, but it's going to go all the way down. That's going to go all the way back to B. So really, we could just get rid of this left part right here. That's not important to us. So the Thevenin equivalent circuit is 3.9K. Look at that. Okay. So step 1 is done. Step 2 is done. Step 3, find V Thevenin. The first step for finding V Thevenin is removing the load resistor. So let's do that. All right. Let's make this an open circuit. V Thevenin. Okay. Now, since this is an open circuit, we're not going to have any current flowing through here. No current is going to flow this way because current cannot flow through an infinite resistance. It's always going to choose the path of least resistance. So it's all going to flow this way. Since no current is flowing to the right and all of it is flowing to the left, V Thevenin is then equal to this node right here. This node, right? And this node you can very clearly see because of the DC voltage source that V Thevenin is going to be equal to negative 8 volts. Look at that. No algebra required. I told you guys that this was an easy one. Put it all together and find V out. Okay, so V Thevenin, well, we can actually switch this around because it's -8, so plus minus 8. Our Thevenin, yeah, these are both 3.9K. Load is also 3.9K. Okay, and now we, because we need to find V out for the first one, we need to find the current through this. So I equals V over R. This is going to be -8 over, what's 3.9K plus 3.9K? Let's get out my calculator. This is 7 equals, all right, so -8 over 7,800. So that's -0.001 amps. That is, yeah, that's going to be -1 milliamps. Okay. Now if we go here, scroll all the way back up to the top, V out is going to be equal to 1 times I believe that's going to be -3.99, which is -4 volts. Okay. Example 1 is done. Super easy. All right, guys, let's do one more example, and then you're pretty much going to be pros at Thevenin's theorem. Okay, so let's just get right into it. So find the load resistor. Easy, it's right here on the right. 2 ohms, right? Because your load current is flowing across it. All right, step 1 done. Find our Thevenin. Should know what to do here, right? We're going to short our voltage and open our current. All right, clean that up a little bit. Oops, deleted that, but that's fine. Let's go back up here. Okay, it looks like, let's see. All right, so it looks like this 8 and that 5 are in parallel, and they're going to be in series with that other 8 resistor. Oh, and you know what? I could remove this as well. I kind of got ahead of myself there. All right, take out the load resistor. Yeah, so here we go. 8, which is going to be in parallel with 5, plus the other 8 ohm. So we can do this. We can solve it like this. 1 over 8 to the -1 plus 8 equals, let me get out my calculator. All right, putting all that in my calculator, I got 11.08 ohms. Okay. Our Thevenin is done. Now find V Thevenin. Well, we're going to remove the load resistor once again. Every single one of these steps, you remove the load resistor. And V Thevenin is going to be this open right here. Let's see here. How are we going to solve for this? Well, actually, it looks like since going this way is an open current, I'm sorry, since going that way is an open circuit, no current's going to be flowing there. So it looks like if we just label this VA, VC over here. So it looks like node VC is going to be equal to VB. So if we just find node VB, we'll find V Thevenin. Right? Yeah. Yeah, so let's solve for node VB here. Okay, so everything going into B is going to be positive, and all the current leaving it is going to be negative. So this could be I1. This is going to be I2. And going this way, It's going to be I3. No current is flowing over that 8 ohm resistor, so we just need it going over 5. All right, so we have I1 plus I2 minus I3 equals 0. We just need one nodal equation since we're only solving for one node. Right, pretty convenient. So I1, we have 24, so 24 minus VB over 8 plus I2 is 2 amps minus, what is I3 going to be? VB minus 0 over 5, right, equals 0. Basically minus VB over 5. Let's see. Now we're going to, let me just write this again. Actually, no, I don't need to do that. So we could just clean this up a little bit. Minus 0. Right, okay. Now we just have one variable to solve for. And we can get rid of the 8 and the 5 by multiplying everything by 40, right? So 40 divided by 8 is 5. So 5 plus 80 minus 8 equals 0. Okay, pretty convenient. All right, so let's distribute that 5. So 5 times 24 is 120. Equals 0. So we're going to have 120 plus 80, which is 200. I don't know why I had to type that in my calculator. That's 8 plus 5 is 13, right? Which means VB equals 200 over 13, which is 15.4 volts. And this is going to equal V Thevenin, right? Yeah. Cool. Yep, that's V Thevenin, and now we have everything that we need. And we're solving for the I load. Let me get rid of this. This is from the previous example here. All right, so V Thevenin is 15.4 volts. Switch the sign because this is now positive. Well, I know I remember our load is 2, and our Thevenin I think is was it 11? Yeah, 11.08, and that was 2. All right, and now if we just solve for the current in this circuit, we'll have it for the top as well. So let's do it. Because let's see, I equals voltage over resistance equals 15.4 over, let me just put this here, 15.4 over 13 1.4. I got 1.4 amps, and that's it. That's the answer. All right, guys, that's it for today. Thank you for tuning in.